what we're going to be doing today is taking the simplifying radical stuff from yesterday and applying it to variables. Now we're still going to have some numbers here that we're going to have to work with when we simplify some of these radicals, but the focus today is going to be on variables. So just recall simplified radical form, which we are going to abbreviate from time to time again, SRF. What that means is that there are no more square roots, cube roots, or fourth roots, or whatever root we're taking left to find, and no radicals in the denominator. Now in Algebra 2, we did simplify radicals with variables in them, and we just assumed that all variables were positive. This year, we're going to not assume that all variables are positive, and what that will mean is that in some instances we have to add absolute value bars. The beautiful thing is that when you're taking an odd root, third root, fifth root, so on, you can take the odd root of a negative number, so we have nothing extra to do. You can take the odd root of a negative number. So we're going to do what we normally would do. But if we're having an even root, because remember you can't take the square root of a negative number. That's one of the very first things we learned about square roots. And that applies to all even roots. So if we're taking an even root of a variable that is even, and the result is odd, then we have to add absolute value bars. So if you take an even root of an even power variable and the result is an odd power, must have absolute value bars around the variable. And I'm going to fix my handwriting up here real quick. So when we look at these examples down here, I will show you why that is true. Any other time we do an even root, if we don't have this exact situation, we don't need to add any absolute value bars. We just do the process as normal. So example number 1 right here, we have the square root of 20x to the 5th. Well, the square root of 20, we can work with that as 4 and 5. I'm going to leave x to the 5th there. So now we have 2x to the 5th. Or 2 times the square root of 5x to the 5th. So now what we would need to do to figure out how to deal with the square root of x to the 5th, we need to divide this by our index. Now remember, if there's no number there, it's an invisible 2. This is our index. So I'm going to divide the exponent of 5, divide that by 2, and we get 2 with a remainder of 1. So what this means is that x squared, because it went in 2 times, is going to come out of our radicals. So we have 2x squared. And under the square root, we still have 5. And we have x to the first power. Let's see. So we're going to be dividing and looking for a remainder. So again, we took x to the 5th power. That exponent was 5. We divided that by our index, which was 2. And then our quotient or result came out, and our remainder stayed on the inside. So now this one, it's the third root. So we're going to break up 24 into the third root of 8 and the third root of 3x to the 8th power. So now the third root of 8 is 2. And, whoops, I forgot the third root right here. We're going to divide 8, because that is our exponent right here. 8 divided by our index, which is 3. Oops. 3 divided by 8, we get 2. 2 times 3 is 6. Subtract our remainder is 2. So we're going to have x squared come out because our quotient is 2, but left on the inside of our cube root is going to be 3x squared because our remainder was 2. And that would be our simplified radical form. Right, example 3. We have the square root of 50x to the 6th power. Well, we know that 50 can be written as 25 times 2. So now we get square root of 25 is 5, but we have 6, x to the 6th power, and we're taking the square root. Well, 6 divided by 2 is 3, so we have x to the 3rd power. There's no remainder, so we don't leave anything inside the square root, and times the square root of 2. Now, we had an even root, an even power, which was x to the 6th inside the square root, and then our result was an odd power. So we have to have absolute value brackets around it, because these two things should be equivalent for all values of x. And if we go and look at the calculator real quick, I'm going to plug in a negative number for x. Okay, so if we do the square root of 50 times negative 2 to the 6th power, we get that decimal. Now, if I plug in negative 2 to my simplified version down here, 5 times x, which was negative 2, raised to the 3rd power, times the square root of 2, you see it's different. It's the exact same numerals, but we have a negative in front if we plug it into the simplified version. So in order to fix that, we put the absolute value bars around the x to the 3rd power, because that will change that part to positive. So you must have these absolute value bars. So our final answer, written a little bit more neatly, will be 5 times the absolute value of x to the 3rd times the square root of 2. Right, now number 4 right here, we have the 4th root of x to the 8th, or sorry, 8x to the 4th power. Well, when you have a fourth root, this whole thing is being raised to the fourth power. So we're going to treat that as just like one variable, one x. So the fourth root and the fourth power would cancel. So we would have 8x. However, you need to remember that 1 is an odd number in that there's an invisible 1 exponent right here. So we had an even root, an even exponent inside the root, and then an odd variable, an odd exponent once we were done. So we need to have absolute value bars around that x. Again, it only applies when you have an even root, an even exponent under the radical, and your result has an odd exponent. So in example 5, we have two radicals, two square roots to be exact, being multiplied together. So what we'll do is we'll multiply them first to make it under one square root, and we can do that because they are two separate square roots. The index is both 2 for both of these, and it's a multiplication problem. So we can combine that, using our rules of exponents. 10 times 20 is 200. Then we have x to the fourth times x squared, that is x to the sixth power. And then y to the sixth times y to the fifth is y to the 11th. So again, our index is 2. So the square root of 200, that can be broken up into 100 times 2. And then we have x to the sixth times y to the 11th. So now I'm going to start bringing things out. The square root of 100 is 10. The square root of 2 I can't do anything with that, so I'm going to put that down here. Now x to the sixth. 6 divided by the invisible 2 is 3. And then there's no remainder, so we don't have an x under the square root. Then finally we have y to the 11th. 11 divided by 2 is 5, so y to the 5th comes out, but our remainder, when we divide 11 by 2, we have 1 left over, so y to the first power stays under the square root. Now I want to go and double check that all my variables are okay. I started out with an even exponent and an even radical, an even index, and then I ended up with an odd exponent. So that means I need to put absolute values around x to the third. Now for y, we had an even root, but we started with an odd exponent, so we don't need to do anything with the y's. So our final answer is going to be 10. Then the absolute value of x to the third times y to the fifth times the square root of 2y. And we do not need to write a 1 for y to the first power. Now this one looks really ugly. So first we're going to make it under one radical. 20 times 10 is 200. Then x to the third times x to the seventh is x to the 10th power. A squared times a to the fourth is a to the sixth. B to the fourth times b to the sixth is b to the 10th. And then c to the fifth times c to the fourth is c to the 9th. So before we go any further, I'm just going to note that our index is 2. So we have an even index. And if we go and look at our variables and the exponents attached to those variables, we have 10, 6, and 10, which are all even numbers. So that means if I get an odd exponent after I bring them out of the square root, I need to have absolute value bars. This 9, don't need to worry about it. So now let's actually simplify this. We know that from the previous problem that the square root of 200 is 10, and then the square root of 2. I'm going to give myself plenty of space here because we have 4 variables. Then let's work with the x. Our exponent's 10. 10 divided by our index, which is 2, is 5. There's no remainders, so we're going to have x to the 5th power. Well, because it came out as an odd exponent, we need absolute values because we had an even root and even original exponent. Then a, we're going to have 6 divided by 2 is 3, so a to the 3rd. Absolute values bars around that. No remainder. B to the 10th. 10 divided by 2 is 5, so b to the 5th. Absolute value bars around that because 5 is odd, and we had even and even. And now c to the 9th. 9 is odd, so when we do 9 divided by 2 and get 4, we do not need to put absolute value bars around it. Our remainder, though, when we divide 9 by 2 is 1, so we have to put c in the square root. So that is your final answer with those 3 variables that have absolute values, absolute value bars there. And you know, I agree that it looks pretty ugly, but if you just take one piece at a time, we do our numerals first, then we did our x's, then we did a, b, c, and kind of attack it one bit at a time, then it becomes much more manageable. All right, I'm going to do number 9 next, and then I'm going to have you try 7 and 8. So number 9, we are in 4th root land, and 4 is an even number, so we have even root. And what we can do, because they're both the 4th roots, we can combine this into one radical. You may say, well, why would we want to do that? Well, if we have it under one radical, we can cancel things out using simplifying fractions, simplifying variables with exponents. So here we have 16 divided by 2. Well, 16 divided by 2 is 8. Okay, so 8. 4 should go here. So we have the 4th root of 8. And then b over b to the 4th, b over b to the 5th, if you subtract the exponents, 5 minus 1 is 4. The bigger number was in the denominator, so we leave it down there. Okay, so now we can do the 4th root of 8 over the 4th root of b to the 4th. Well, the nice thing about the 4th root of b to the 4th is that the 4th root and 4th powers cancel, and we are now left with the 4th root of 8 over b. Well, and now let's double check. We had an even root, the 4th root of b to the 4th power, which is even, so we need those absolute value bars around b to the 1st power. So by doing it this way and combining our 2 radicals, we did not have to rationalize the denominator. Whereas if you didn't simplify it, you'd have to rationalize at the beginning and then simplify it later on. That would have worked. You would have gotten the right answer. I just didn't want to rationalize a denominator, so I decided to do it this way. All right, so go ahead, try problems number 7 and 8, and once you're done, let me unpause it and see if you got the same answers I did. All right, so for number 7, once you combine those, you have the square root of x to the 12th, and then 12 divided by 2, because we're taking the square root, is 6. And you may say, well, do I got to put absolute value bars around this? No, you don't, because we started out with an even root, 2, an even exponent, but my answer was also even. So we don't need absolute value bars around that. The reason for that is because anything to an even power would give you a positive result. So any negative number raised to the 6th power will give you a positive number, so we don't need absolute value around it. But in number 8 over here, we did the 4th root of 16, which is 2. And then for x, 16 divided by 4 is 4 with no remainder. And because 4 is even, a result our x to the fourth that came out as an even exponent, we don't need absolute value bars. Y to the 12th, 12 divided by 4 is 3. Well, even root 4 divided by even number 12 gave us an odd result, so we need absolute value bars. So the more that you do these, you will be able to do them very quickly. You'll get good at looking at each part individually and then combining it all at the end. So thanks for watching the video. Make sure to smash that like button and subscribe.